So now we discuss sampling. This is the first step in digitizing an analog signal. So it's related. So since we want to discuss the digital communication systems in the coming lectures, so sampling is the first step to digitize an analog signal. So as I said, we can digitize analog signal through sampling, and after that we perform quantization. So we'll look into this in different videos. So it basically analog to digital conversion ADC sets the foundation of modern digital communication systems. The sampling rate must be chosen large enough to permit the analog signal to be reconstructed from the samples with sufficient accuracy. So for this we have the sampling theorem. It determines the sampling rate for obtaining lossless sampling. So what we mean by lossless is that when we convert an analog signal to a digital signal, the information should be kept intact. So, and when we perform digital to analog conversion, so the analog signal should be a close copy of the original analog signal. So sampling theorem has a huge role in signal processing and communication theory. So what is the sampling theorem? So here we have as an example, we have a figure where we have an analog signal GT. It's varying with respect to time. So if we take the Fourier transform of this signal, so this should be a band limited signal whose bandwidth is equal to b hertz. So outside this bandwidth the signal has a value of 0. So if I plot this situation, let's say this is the frequency, and if I'm plotting this as it looks like a low pass signal, here we have the bandwidth b. So this is what we mean by a band limited signal having a bandwidth of b. Now let's say r samples per second represent the uniform discrete time samples of gt. So when we sample this gt, let's say the rate is r samples per second. So from the Nyquist criteria we know that the sampling rate, the number of samples per second, should be twice the bandwidth of this signal. So basically Nyquist rate says that the sampling rate should be twice the maximum frequency. In this case the maximum frequency is b. So here we have a plot of this signal. So this is just a representation. It's the Fourier transform of the signal gt, which is equal to gf. This is the amplitude in terms of omega radian per second. These are the frequency ranges. In terms of frequency, our bandwidth is from 0 to b. So how we perform sampling is we multiply an impulse train with the analog signal gt in the time domain, and in this way we get a sampled version of gt, right? So these samples, if they have a rate in frequency domain, if they have a rate of 2b, then it means the reciprocal of frequency 1 over fs is equal to 2s. It gives us the time between two samples, right? So this is how the sampled signal looks like. We have represented it with a dash just to differentiate it from gt. The samples are taken at the time period of ts seconds, and so by substituting values of n, we can get every other sample, every next sample. So since we had multiplied an impulse train, so you can see each sample is represented in the form of an impulse. So the relationship between the sampled signal g dash t and the original analog signal is shown here. So we can see this is the original analog signal gt. It is multiplied in the time domain with the impulse series of impulses, which is a periodic signal. So as you can see, this is a periodic signal, the sequence of impulses. When it is multiplied, we get an output mathematically equal to this. So all the values of gt at nts, where we have an impulse, all those values are multiplied with the impulses at different instants nts. So that means if you look at this, this is the amplitude of gt at this particular location in time. It could be 4ts, 5ts, or simply nts, the location of the time axis. So because the impulse train is periodic, as we said, and it has a period of ts, it can be expressed as an exponential Fourier series. We know Fourier series is for periodic signals. So this is the impulse train representation, delta ts. In terms of Fourier series, we have 1 over ts, the time period of the periodic signal, and then we have the exponential series e raised power j n omega st. N is from minus infinity to infinity, because we have a continuous samples from minus infinity to infinity, and this is the Fourier series representation of our signal, this one, the impulse train. So that means this product of the signal gt with the impulse train, if we multiply gt with this delta ts, we get this expression where you can see we have substituted gt over in this place, right? So that is the resulting sampled signal. So it represents the samples of the signal gt, and we have denoted it through by using g dash over here. So how does the spectrum now looks like? This is the question. So the spectrum of g dash t, we can get it by taking the Fourier transform of gt, and this is how the spectrum of g dash t looks like. So there should be a dash here. This is done through frequency shifting property of the Fourier transform. So we know from the frequency shifting property that if two signals are multiplied in the time domain, they are convolved in the frequency domain. So if we look at this, this is the frequency domain of gt, and this is the time domain of delta t. So we know the Fourier transform of a periodic series of impulses is also periodic impulses in the Fourier domain, right, in the frequency domain as well, and the distance between these impulses, frequency distance, is equal to fs, right? So this is, we know from the Fourier transform. So when this signal is multiplied in time domain with gt, so then that means this one, Fourier transform of the two are convolved, and because of this convolution, at every location of an impulse we will have this spectrum of gf repeating at these locations, and this is why we get this plot here where you can see the fundamental spectrum is shown here, the actual one, and it is repeated at every fs, because in the frequency domain we have convolution of the two terms that were being multiplied in the time domain. So this is how we represent this whole spectrum gf. You can see 1 over ts, gf minus nfs, which means that by substituting values of n, we will get the the location of the spectrum at that point. So this means that the spectrum of gf consists of the spectrum of gf, which was this one, scaled by a constant 1 over ts, so there is a multiplying factor as well, repeating periodically at fs. So this is how the spectrum of g dash f looks like after the sampling. Now the next thing is, can we reconstruct gt back from g dash t without any loss of distortion? So the answer of this question lies in this spectral plot. So as you can see, the spectrum of gf is only this part. So if we can if we can use a low pass filter that can separate this spectrum, so that means at the output of the low pass filter we should get GT. So this is the process of reconstruction. Perfect recovery is possible if there is no overlap among replicas. So that means if the distance between these 2 points, this point and this, if they do not overlap, if this spectrum does not overlap with this one, then we can easily reconstruct the signal. We can easily use a low pass filter to filter it out, right? So how can this condition of no overlap be satisfied? So you can see if this Fs is greater than 2b, so this is 1b, this distance, this spectrum width, and this spectrum width is also 1b, so that is equal to 2b. If this Fs is greater than 2b, then we will have this region where there is no spectral components, and that means we can easily filter this out. So from this spectrum we get this definition that sampling frequency should be twice of 2b, at least should be greater than twice of 2b. So the greater this sampling frequency is, the easier it is for us to design a filter that can filter out the spectrum of GF, right? So if we take the reciprocal, it gives us the time period between the samples, and that should be less than 1 over 2b. So as long as the sampling frequency Fs is greater than twice the bandwidth of b in hertz, we can reconstruct G f from G dash f, right? So when this is true, GT can be recovered through an ideal low pass filter of bandwidth b. So we can have a practical low pass filter as well, but ideal low pass filter means that our the roll off is very sharp, like this. It's like a rectangular filter. But if we have a larger Fs, then we can afford to have a lesser sharp roll off, and so the filter would be more practical, right? So this sampling rate of at least is equal to 2b, twice the maximum frequency, is called the Nyquist rate, and the distance between two samples in time is called the Nyquist interval for this low pass signal GT. So we now discuss the signal reconstruction process. So the reconstruction is also called interpolation, because we actually, when we have different samples, we just combine them, and the region between the samples is interpolated, right? So the sample signal contains these components 1 over 2 TS GT. So let's look at the sample signal. This is the sample signal. You can see it has this component 1 over TS, and it has this GT as well. So that is why it says 1 over TS GT. And to recover GT from or GF from the sample signal, this is the sample signal in time. This must be sent through an ideal low pass filter of bandwidth B, so that, and the filter must have a gain of TS, because in the sample signal we have 1 over TS. When it gets multiplied with TS, so we are left with 1. So this low pass filter, as we said previously, it should have a rectangular shape. An ideal low pass filter has a rectangular shape. So we have this function rect, and it's omega by 4 pi b in terms of radian frequency. In terms of hertz, it's f by 2b. So 2b, as we know, this rectangular function, it's the width of this rectangle. So to give an idea of how the rectangle and sink are related, so this is so in this case the rectangle is in the frequency domain. So let's look at this rectangle, which is in the frequency domain, and it has rect TF. So this F lies here. So in this case, if we compare this expression with this one, we know that this T is equal to 1 over 2b, right? So that means the width is 1 over t minus 1 over t for this one, and that means in this case the width is b and minus b. So these plots are shown just to show the relation between a rectangle. Now the frequency domain of this is a sinc, or if we have a rectangle in the time, we take the Fourier transform, we get sinc in the frequency. So this is the dual relation between the sinc and the rectangle. So that means, as we said, by using a low pass filter that has a rectangular shape, we can extract our signal. So this is that low pass filter. From B to minus B is the total width of this filter, and this filter looks like this. If the inverse transform in time domain, it looks like a sinc function, and from these plots we know that the width here should be t by 2, and the width here should be minus t by 2. The point here is t by 2 and minus t by 2, and that's why we have 1 over 2b and 1 over minus 1 over 2b at these points, like the main lobe intersections with the time axis. So ideal interpolation filter is shown here, HF in frequency domain. Its time domain is equal to this. So this is a sinc function 2 pi bt. So its time domain is here. So when we consider these variables, as we said, t is 1 over 2b. When we substitute these values, we get a sinc function that has 2bts, and it has sinc 2 pi bt, and that plot looks like this. So assuming the use of Nyquist sampling rate, which means that ts is equal to, so the Nyquist sampling rate is this one, ts is equal to 1 over 2b. So if we substitute that over here, ts is 1 over 2b, so this term becomes 1, and we are left with the impulse function. So what we show in this plot is that the filter, a rectangular filter in frequency domain, can be used to reconstruct the signal when impulse train sampling is used. The impulse response, or the time domain shape of a rectangular filter, looks like this. The expression for that shape, the sinc function, is over here, right? So now it would be interesting to see for every sample, like we can extract this signal as we show here. We can just use a simple low pass filter, rectangular filter, and we can see that the shape at the output of the spectrum of this signal is exactly equal to the spectrum of this GF, this one. So it means we got our signal back. But how does this look in the time domain? So in the time domain, we have impulses of different amplitudes. So if we pass it through a filter, in the frequency domain it's rectangle, but in the time domain the impulse response should be plotted for at each of these points, and the impulse response, as we just discussed, for a rectangular filter is a sinc. So that means all these points are replaced with a sinc. So a sinc has many points, so just like this. So as you can see, this impulse has been replaced with a sinc, this impulse has been replaced with a sinc and a sinc, so and a sinc. And you can see the interesting thing is that when we add these impulses, so at this point only one amplitude exists, this one. The rest of them, the higher lobes of every sinc function is 0 at this point. Again, at this point only this sinc function maximum lobe exists, and all the other points and all the other contributions from the impulses are from the sinc functions are 0. So if we add them, if we add these sinc functions, you can see this is going down, this one is going up, So when we add them, we get a line like this. So this is how we have proved that the signal, the reconstructed signal in the time domain, is sum of the sinc functions that are obtained uh, as an impulse response of these impulses of different amplitudes, right? So then let's give it some mathematical formulation. So the kth sample, let's say, of this input gt is the impulse. So this is, let's say, one of the impulse that we are considering. So this is equal to kts, so the amplitude of g at this point, and then we have a delta, an impulse at this point, right? So the filter output of this impulse is, now this will have an impulse response ht, impulse response, and this complete signal gt, as we saw in this plot, is the sum of all the impulse responses, right? So in this case, h is the impulse response, is a sinc function, as we saw previously, because the filter is a rectangular filter in the frequency domain. So in the time domain we have a sinc function. So all these impulse responses are added and we get our signal gt. When we just multiply this 2 pi b inside, we are left with this expression 2 pi bt minus k pi. So we have discussed the impulse train sampling, and we have proved that this can be reconstructed by, we can get our signal back from the samples by just passing it through a low pass filter, which will give us the exact spectrum. And we have seen that the low pass filter has an impulse response of a sinc. All these sincs can be combined to get the signal back gt. So this is the summary. We discussed sampling theorem, signal reconstruction, and we saw how the practical signal reconstruction takes place.